Hello, my name is Georgis Georgiakoudis and I am a computer scientist at the Lawrence Livermore National Laboratory. I will be talking to you about PyOMP, which is our Python compiler for implementing OpenMP parallel programming in Python. I would like to mention my collaborators for this work. These are Todd Anderson from Bodo AI, Stuart Archibald from the Numba team in Anaconda, Bronis Desupinski from Lawrence Livermore, and Tim Matson from Merli AI. So OpenMP is a widely used portable parallel programming model for CPUs and GPUs. Python is the number one programming language by popularity based on the TIOBE index, and it offers high productivity and an extensive software ecosystem. And Numba is an easy to use, fast and extensible JIT compiler for fast Python execution. So what PyOMP does is that it combines these technologies to provide high performance OpenMP parallel programming in Python compiled through Numba. Particularly in Python, the parallel programming software ecosystem is highly fragmented. There is no easy-to-use, general, high-performance solution that allows writing a custom parallel algorithm in Python and executing it fast. For that, we believe the OpenMP is the best solution. It has decades of proven usability and performance, and for us, this is the right approach. The implementation of OpenMP in PyOMP is designed to reuse familiar OpenMP syntax but do it in a Pythonic way, using Numba to compile Python code for fast execution. This is a very basic example of a parallel hello world program. Dissecting the code, the programmer first imports the Numba OpenMP modules that implement JIT compilation, the OpenMP context manager, and any OpenMP runtime functions. Then there is the hello function, which is decorated for JIT compilation, and OpenMP regions are defined using with statements and the OpenMP context manager, where the programmer provides the OpenMP directive along with any clauses to the context. In this case, the parallel directive. The body of the context forms the OpenMP construct. In this case, each thread is going to print hello with the global thread ID. PyOMP supports what is known as the common core of OpenMP, including widely used directives and clauses that implement SPMD, work sharing, and task-based parallel programming constructs for CPUs. And also commonly used directives for GPU offloading, which include constructs to set up the device data environment, mapping data between the host and the device, and implementing parallel execution on the GPU device. We show also a more complicated example of calculating pi using numerical integration with PyOMP on the GPU. It starts again with the necessary imports and decorating the computation function for JIT compilation. In this case, there are two OpenMP regions. The outer one creates the offloaded target region for the GPU, and the nested one uses the loop directive, which translates to an equivalent teams distribute parallel for construct for executing the following loop by distributing iterations across teams and threads on the device and using a reduction to accumulate partial sums. PyOMP is implemented as an extension to Numba, which itself uses LLVM to compile Python. PyOMP adds an OpenMP parser that lowers OpenMP regions to Numba IR nodes, which are then lowered to LLVM IR with PyOMP defined OpenMP intrinsics. A final PyOMP LLVM pass converts these intrinsics into executable code targeting the LLVM OpenMP runtime. For GPU support, PyOMP adopts split compilation, building device and host code separately, embedding the device binary in the host, which then loads and launches OpenMP GPU kernels through the OpenMP runtime. We provide more details in this compilation process next. We'll walk through a small example to show the compilation process using target offloading. Say we have an example kernel as the one at the top, which offloads a computation that increments element-wise a vector by 1. PyOMP extending number parses the directive in the context and emits OpenMP number IR nodes that mark the start and the end of the region, enclosing the region body. The start region marker includes the information of the OpenMP region using tags, and those tags store the directive and its clauses, including data set attributes for variables, for example, and the mapping of the array. In this case, the array is a NumPy array, so we also include metadata such as its shape and stride. Following, PyOMP lowers those region markers to calls to LLVM intrinsic functions, marking again the entry and exit of the OpenMP region that encloses the body. In this LLVM-IR format, the same information for directives and clauses is stored as operand bundles to be parsed by PyOMP's LLVM pass. With split compilation, PyOMP first builds device LLVM-IR, which is lowered through PyOMP's LLVM pass into executable IR using calls to the OpenMP device runtime for parallel execution, distributing work across teams and threads. The resulting binary image is embedded in the host LLVM-IR, which will lower the target region intrinsics for managing offloading to load and execute from the image. After compilation, Naba executes the host binary, which loads and launches device kernels. For CPU-only parallelism, PyOMP follows a similar process but compiles only the host path for parallel execution without split compilation. We evaluate PyOMP on the more challenging use case of GPU programming using programs from Checkbench, the Heterogeneous Computing Benchmark Suite. We compare C, C++, OpenMP offload implementations of those programs with equivalent feature-full implementations using PyOMP. The hardware is an NVIDIA 800 GPU and the software is Python 3.9, Numba 0571 based on LLVM 14 and CUDA 12.2. The comparison metrics include kernel execution time that measures code generation quality, data transfers, and JIT compilation latency. We provide more details about those performance measurements in our recent PyOMP 2025 paper. Looking at kernel execution times, PyOMP is overall competitive with the C++ versions. In certain cases, PyOMP is even faster because of whole program visibility optimizations thanks to JIT compilation that are not enabled by default in ahead of time C++ compilation. In one case, the HackMK kernel, PyOMP generated code is slightly slower by missing fused multiply add optimizations, but we've resolved this issue in the latest implementations of PyOMP by enabling more aggressive optimization in Numba's LLVM backend. We next contrast data transfer size between the host and the device. C++ mainly transfers data from bare pointers, whereas in PyOMP we also transfer metadata for data containers. For example, the shape and stride of NumPy arrays. We notice that those metadata are very little to make a difference, and the size of transferred data in both versions is comparable. Interestingly, in one case, LavaMD, we even found that PyOMP transfers less data by avoiding transferring unused fields from a structure of arrays in the target region. Regarding data transfer times, PyOMP has more noticeable overhead due to the implementation transferring each metadata element as an explicit separate memory copy. Nevertheless, setting up the data environment is usually a one-off operation followed by lengthy GPU computation which amortizes such overheads. Also, we are improving our implementation by coalescing these copies. We also measured the JIT compilation time in PyOMP and contrasted with the ahead-of-time compilation in the C++ version. We observed JIT compilation through Python is understandably slower, but Numba already provides caching which mitigates those overheads. PyOMP is developed open source and it is available to use. Our repository is in GitHub and we provide installation packages both through pip or conda. We welcome user feedback, so please feel free to use it and contact us. Concluding, PyOMP brings OpenMP parallel programming for CPUs and GPUs to Python. It is implemented on top of production-level infrastructure, the Numba JIT compiler and LLVM. It does show competitive performance compared with C++. Inspired by PyOMP, OpenMP has started a Python language subcommittee and we are working within it to make Python officially supported by OpenMP. Thank you very much and I hope you enjoyed this presentation. Feel free to reach out for questions or feedback.